Okay, I think we're recording. So let's get started in 6.3. Oh, let me start the timer. So we've spent the past couple days doing some basics of counting and combinatorics, and then we've spent a very fun chunk doing pigeonhole principle exercises. Very fun for me. I don't know how you feel about them. I haven't had very much opportunity to gauge the crowd, so to speak. So okay, we've done pigeonhole principle and general counting. So now we're going to do permutations and combinations. This is section 6.3. So the permutation stuff should be pretty familiar. Um, it's when we start getting into the combinations that things become a little more interesting and novel. One second. Is my dog cam working all right? Okay, I guess that's what we get to see. Okay, so a permutation is a way of counting arrangements where order matters. Or as a permutation is an arrangement where order matters. So for instance, if we want to count, I mean, we've already done this exercise, but count number of ways of assigning 3 people an office each if there are 5 offices. So I could have person 1, person 2, and person 3. And then if I assign to each person an office, like person 1 gets office 4, person 2 gets office 1, and person 3 gets office 3, this is going to be a permutation because the order matters. 413 is not the same as 314 or 341 or any of the other ways of choosing a subset of 3 offices from 5 offices, right? Here the order matters. Okay, so we're going to just write this up as a theorem. So, and I'm not really saying anything new here. If n is in z greater than 0, so n some positive integer, and 1 is less than or equal to r and is less than or equal to n, then there are PNR, this symbol denotes the number of R permutations from n elements, equals n times n minus 1 all the way down to n minus r plus 1 R permutations of a set with n distinct elements. So here, an n permutation means that, or an R permutation of a set with n elements is an ordered collection of R distinct elements of n. So for instance here, this is a 3 permutation of a set with 5 elements, namely the 5 offices, where I keep track of the order that I took out 4, 1, and 3. So this is a different 3 permutation of this set than 1, 3, 4. And the proof is that this is just the product rule in combinatorics. Namely, how many choices do you have for the first element of your R permutation? Well, if your set is of size n, then there are n elements for your first choice. then how many choices are there for your second element of your R permutation? Well, n minus 1, and so on and so forth. So there are precisely R terms here, R terms. In particular, if I were looking for a 2 permutation of a set of size n, then I would have n choices for the first one and n minus 1 choices for the second one. Okay. So the point is that I want to write this in a manner that will be kind of helpful when we start looking at combinations. So recall factorial notation. So factorials is if I have n in z greater than or equal to 0, I'll make two cases. Either n is greater than 0, and then n factorial is equal to n times, oh, I didn't leave myself enough space, n minus 1 all the way down to 2 times 1. So it's the product of all of the integers less than n, including n. And then if n is equal to 0, then 0 factorial is equal to 1. So this is a reasonable way to define 0 factorial because why do I want to say that this is a reasonable choice? We think of n factorial as a way of how do I want to say this? This should be a way of choosing 0 elements from a subset of order n, of cardinality n. So there's exactly one way to choose 0 elements. Maybe that's one way to approach understanding why 0 factorial should be equal to 1. That's probably not very satisfying because we haven't really gotten to choosing in combinatorics. So for the moment, let me just say that I define 0 factorial to be 1, and we can discuss this more later. It's kind of a gap on my part. Okay, in any case, let's use this to rewrite our theorem. So now a corollary of the theorem is that the set, the collection of, or the size of the number of R permutations in a set of n elements, namely P n R, is equal to n factorial over n minus R factorial. This is exactly just looking at this and saying, well, this expression, n times n minus 1 all the way down to n minus R plus 1, that looks exactly like n factorial, where I chop off all the stuff here that goes down to n minus R minus 1, all the way down to 2 and 1, right? This expression right here is exactly n minus R factorial. And if I take n factorial, which is this whole thing, and then divide by n minus R factorial, I'm left with exactly this expression. So another way to write the number of R permutations of a set n is exactly n factorial over n minus R factorial. Okay, so we're already kind of experienced with R permutations because it's just essentially the product rule in combinatorics, but I'll do another example just for fun. So as an exercise, how many permutations of the set A, B, C, D, E, F, G, H contain the string ABC as an unbroken string? Right, so a permutation of this set is essentially a choice of ordering of this set. And I'm looking for an ordering of this set such that A, B, and C form a string. And this is not so difficult to figure out. What we do is we treat ABC as its own symbol. So we can call this symbol 1. And then D will be symbol 2, 3, 4, 5, 6. And so if I want strings where ABC appears as a unbroken string, that's the same as just treating this as a symbol and looking at permutations of a set of size 6, where wherever I put a 1, I just replace it with the full string ABC. And so we're looking for the 6 permutations of a set of size 6. So namely, I'm looking for P of 6, comma 6. So this is a 6 permutation of a set with 6 elements. And this is going to be equal to 6 factorial over 6 minus 6 factorial, which is equal to 6 factorial over 0 factorial, which is equal to 6 factorial over 1, which is equal to 6 factorial. And this isn't saying anything new here. I'm just re-expressing in terms of the factorial language or this permutation language what we're doing here. And essentially, we're just choosing an ordering of these numbers 1, 2, 3, 4, 5, 6. And then once we've chosen an ordering, we're swapping out 1 for ABC, we're swapping out 2 for D, 3 for E, etc. And the answer should be 6 factorial because there are 6 symbols that you choose from. Namely, you can choose the 1, 2, 3, 4, 5, 6. Then there are 5 symbols to go in the second spot, 4 symbols to go in the next spot, 3 symbols to go in the next spot, 2 symbols to go in the next spot, and then you're left with 1. So from the product rule, we can immediately compute this. And I'm just rewriting it in terms of our number of permutations. Oh, okay. So all that I aim to show with this is that permutations are something that are pretty familiar to us. Now let's talk about combinations. And combinations are arrangements where order does not matter. In other words, if you're looking for some sort of combination or an R combination on a set of n elements, then what you're really looking for is just a subset of size R. And remember, in our definition of subset, there's no notion of ordering. It's just which elements are in and which elements are out. Okay. So what do I want to say? Yes. R combinations in a set of cardinality n just means a subset of cardinality R. Whereas an R permutation in a set of cardinality n means an ordered subset of cardinality R, where you keep track of the ordering of your subset, or you assign an ordering to your subset, say. Okay, theorem. The number of R combinations of an n element set is and I'll give a bunch of notation, it's either written as C of nr, which is what the book uses, combinations of R elements in an n subset. We also use this notation nr. This is read n choose R because the number of R combinations is equivalent to choosing R elements from n, or finding an R element subset of n. So these are the notation, and then this is going to be equal to n factorial over R factorial times n minus R factorial. This is also read n choose R. So you have n elements and you choose R of them. Okay, the proof goes as follows. So the idea is we think about combinations first in terms of permutations. So what you can first do is you can think of a permutation as first taking a combination. First you take an unordered collection of R elements, and then you order them. So in words, P and R, this is R permutations, can be found by first choosing R elements from n, choosing R elements, and then ordering them. So the number of ways to choose R elements from the set is going to be C and R. And then how many ways can I order an R element set? Well, orderings are permutations. So what I'm looking for is an R permutation of R. So an ordering of R elements is the same thing as a permutation R. This is exactly what we were doing up here. This is some way of ordering 6 elements. So what this is saying is that permutations, R permutations of n should be equal to, the number of R permutations of n should be equal to the number of R combinations of n times the ways to mix up and order that set that you picked in the choose. But we have formulas for these two, right? So P and R, this is going to be exactly equal to n factorial over n minus R factorial. And this is going to be equal to the number of ways of choosing an R element subset from a set of order n times, we already know what PRR is. This is R factorial over R minus R factorial. But R minus R factorial is just 1. Oh, I'm sorry, I'm a little off the page. So thus we see that n factorial over n minus R factorial is equal to C n R. I just divided over by R factorial. And we get an expression for the number of ways of choosing an R element subset from a set of order n. And this shows that this number, C n R, or n choose R, is given by this formula. Okay. So now I want to kind of write something up. So something called combinatorial proofs. We won't get much of a chance to practice these or go into these, but a combinatorial proof is when you prove an identity by showing that both sides of the identity count the same thing. Um, I think that the most basic possible example of a combinatorial proof goes something as follows. Like how to show that n times m is equal to m times n if m and n are in z greater than 0. So one way of understanding what's going on here is this is asking me to prove the commutativity of multiplication of integers. And a combinatorial proof of this fact could go something like saying, well, n times m is equal to the number of boxes in an n cross m array of boxes, or rectangle of boxes. So I have some array of boxes where there are n boxes on this side and m boxes on this side. And one way to count them is I do m times n, where each of these is, there are n boxes in each of these vertical columns, and so m times n is I'm saying take m copies of the n boxes. I'm counting it one way. Whereas the other side of the equation should be interpreted as taking strips going this way, where here I have m boxes in each of this horizontal breaking up of what's going on, and then I take n of these, right? So essentially, I have two ways of counting the same object. Either I split it up in terms of m columns of n boxes each, or I split it up into n rows of m boxes each. And since I'm counting the same number, these two things have to be the same. This maybe isn't a very good example of a combinatorial proof, and many more interesting examples arise. This is maybe just the most basic one that one could think of. You're conceiving of the two sides of the equation as counting the same object in two different ways. Okay, let's see. What should we do next? So let's do examples. Suppose that there are 9 math faculty and 11 computer science faculty. And let's say that we want to form a committee with 4 math faculty, or 3 math faculty committee with 3 math and 4 computer science. Okay, well, how many ways are there of choosing such a committee? Here are 2 ways to think about it. One is that we just use our choose notation. Essentially, we need to choose 3 elements from a 9-element set and then choose 4 elements from an 11-element set. So just immediately, this is 9 choose 3 times 11 choose 4, which is equal to 9 factorial over 3 factorial times 6 factorial times 11 factorial over 4 factorial times 7 factorial. And we can simplify this out. So this is 9 times 8 times 7 over 6 times 11 times 10 times 9 times 8 over 4 times 3 times 2 times 1. And so you can simplify these out and get nice forms of answers. But this is a viable answer, right? This is something very computable. Another way of thinking about this is thinking first in terms of permutations. How do I pick a 3 permutation of the 9 math faculty? Well, there are 9 choices for the first math faculty, 8 choices for the second math faculty, 7 math choices for the third math faculty, times 11 choices for the first comp sci faculty, times 10 for the second, times 9 for the third, times 8 for the fourth math faculty. So this is like an ordering of first I order 3 math. This is an R permutation or a 3 permutation of 9, and then this is a 4 permutation of 11. But the point is, it doesn't matter which order I choose the people in, right? A committee, it doesn't matter who is first on the committee. It just matters who are the 3 or 4 people in the committee. So when I divide by 6 over here, I can think of this dividing by 6 as all the ways of scrambling up 3 symbols, right? I picked symbol 1, symbol 2, symbol 3, and then there are 6 ways of ordering those 3 symbols. And since all those different orderings should be treated as the same, I'm going to divide this side by 6. Similarly, this term also appears as first I take a permutation, and then I can view 4 times 3 times 2 times 1 as the number of ways that I can order a 4-element set. And since all those different orderings should be treated the same, I'm going to divide by it so that I don't treat them differently. This count, 11 times 10 times 9 times 8, is looking at all the ways that I can pick an ordered set of 4 professors from comp sci, and then I divide by this to say all of those orders, if you can move from one to the other by changing just the order but not changing the people, then they should be treated the same. So this term right here, this 4 term and this 3 term can be thought of as the ways of scrambling the ones that you did pick in a certain expression. Okay, probably I've talked too long about this. Let's do some more examples. Let's do the following example. How many subsets with more than 2 elements does a set with 100 elements have? 100 elements have. Okay, so first of all, we already know how many subsets a set with 100 elements has, right? So the total number of subsets is 2 to the 100, right? And now if I want to find all the subsets with more than 2 elements, then I want to subtract from this number the number of sets with 2 elements, the number of sets with 1 element, and the number of sets with 0 elements. So a way to think about this is I want to take 2 to the 100 minus 100 choose 2. This is exactly the number of 2-element subsets of a set with 100 elements, minus 100 choose 1. This is precisely the number of one element subsets of 100 minus 100 choose 0. This is precisely the number of subsets of 100 with 0 elements. Okay, and so we can write this out a little more explicitly. 2 to the 100 minus, well, this is going to be 100 factorial over 2 factorial times 98 factorial minus 100 over 1 factorial times 99 factorial, and then minus 100 factorial over 0 factorial times 100 factorial. And let's kind of examine these numbers and check that they make sense. So if I go further, this is 2 to the 100 minus, here I have 100 times 99, I divide by the 98 factorial, all over 2, minus 100, all the tail, the 99, 98, 97, so on and so forth, is taken care of by dividing by 99 factorial, and here I divide by 1. And then here, minus, well, 100 factorial over 100 factorial is 1, and so I have 1 over 0 factorial, which is 1. Let's just check that all these numbers kind of make sense. This is the total number of subsets of a 100 element set. There should be exactly one way of choosing 0 elements from a set of 100 elements. There's no choice to make, there's just one way, you leave all the elements there. There should be 100 ways to pick a 1 element subset of 100. Because there are 100 elements and you pick one. There are 100 ways to do that. Lastly, there are 100 times 99 ways of picking an ordered subset, right? For the first element, I pick element A. For the second element, I pick element B. So there are 100 times 99 ways of getting an ordered subset. And then I divide by 2 because I've counted A, B, and BA as 2 different elements in this 2 permutation, and dividing by 2 says, well, I'm going to treat those 2 as the same. I'm not going to overcount. So this is like the division rule. So indeed, this is the number of 2-element subsets of a set of size 100. And so this is my final answer. With some simplifications if you want. This is like 2 to the 100 minus 5051, maybe? I don't know. Okay. Good. That's another example. What shall we do next? Yeah, let's do this example. This is just the loveliest one we've done in this whole class. How many ways are there for 3 penguins and 4 puffins to stand for a photo if A, all the penguins have to stick together, or B, all the puffins stick together. Okay. Here is an argument that just kind of relies on this intuition that we've been building. Here's one way to count these. For A, well, the first thing that I want to do is if all the penguins are going to stick together, then there are 5 slots, right? 1, 2, 3, 4, 5. And one of the slots is going to be filled by 3 penguins in a row, and then all the other slots are going to be filled in by puffins. So the number of ways to choose where the trio of penguins appear is 5 choose 1. 5 choose 1. I pick one of these slots for where the 3 puffins are going to, or the 3 penguins are going to stand together. Well, all that I've done there is I've just chosen where the three penguins are going to stand together, but I need to figure out all the different ways where I can order the set of puffins and the set of penguins. So there are 3 factorial ways of ordering the 3 penguins, right? I have a 3-element subset and I need to find all the ways of ordering them, and there are 3 factorial ways. And then I also need to find the number of ways of ordering the 4 puffins. And there are 4 factorial ways of doing that. Right? I pick 1 puffin to go in the first available spot. There are 3 choices for puffin 2 to go into the next available spot. There are 2 choices for the last puffin to go in the last available spot, and there are no choices. So like, say that the penguins have decided to go here, then there is 4 choices for which puffin goes here, 3 choices for which puffin goes here, 2 choices for which puffin goes here, and no choices for which puffin goes here. And then in here there are 3 slots, and then there are 3 choices for which penguin goes here, 3 choices for which penguin goes here, or 2 choices for which penguin goes here, and only one choice for which penguin goes here. And it's the same when you switch it from puffins to penguins. So then if all the puffins are going to stick together, then there are 4 slots, and you're going to pick one of the slots for the 4 puffins to occupy. So 4, choose 1. This is which slot the puffins occupy. And then we have 3 factorial. If the puffins are occupying 1 slot, I need to order the penguins in the remaining 3 slots, and then I need to order the puffins in their slot. Great. What a great way to end class. Oh, we're almost done with 381. Almost there.